So I want you to remember this figure because I'm going to need it in the next slide. It's actually going to break down what people were doing prior to deep learning and what are they doing now. And then you're going to start to appreciate what deep learning is actually doing for us. Let's move on. The title is Return of the Devil in the Details. What are the details? What do they mean by the details? Let's divide machine learning into these two major categories: shallow models versus deep models, versus deep neural network type of models. When it comes to deep learning, we do a lot of tricks, right? We do data augmentation. We do dropout. We do, I don't know, batch normalization, all sorts of details. We take our image, we flip it left and right. These are the data augmentation. We add sometimes noise to our images while trying to train a deep neural network. The question is, if you do the same thing to the methodology prior to deep learning, are they also going to benefit? And if yes, is that benefit enough to actually catch up with deep learning and beat it? So the idea of this paper is, let's give shallow models another chance and see what happens. The big picture of both of the methodology, you want to do either feature engineering or feature learning. You take an image, you push it through a function. This function, either you learn it, given enough data, or some smart people are going to spend a lot of time analyzing the statistics of an image and end up with a function that takes as input an image, and it's going to turn it into a vector, featureize it. Let's see what people were doing prior to deep learning. This is one of the methods, and it's a shallow representation. It is improved feature vector, IFV. What would you do? You would extract a lot of patches, and these are dense patches. So you have a sliding window that you push it through your image. So you're going to look at your images in terms of patches. That's going to give you a huge collection. And then you're going to get the corresponding local descriptors. These are scale invariant feature transform. That's what SIFT is standing for. But there is going to be, if I want to go into the details of SIFT, we need to have, I don't know, at least spend 1 week on that with the speed that we are going now. But it has nothing to do with deep learning. But in terms of big picture, what SIFT does is you take that local patch, and then you're going to first find some key points. These key points could be the edges or some points that are really important, have a higher density compared to their neighborhoods. You first find some key points in them. Then you're going to compute some discrete gradients, some finite differencing. They're going to give you some vectors. So you pick a key point, I don't know, somewhere in your image. You look at the neighborhood. In that neighborhood, you're going to look at every single pixel in that neighborhood. And then you're going to look at the finite differences in the x direction and y direction. These are going to give you vectors. Now you're going to have a histogram of all of these vectors in your data set, in your entire data set, not only this particular patch, but your entire data set. And these are a bunch of arrows pointing left, right, up, north, left, south, etc. You're going to create a histogram, and then that histogram is going to give you, after some processing, is going to give you your local descriptors. That's how you're going to take a patch, which is explained in terms of pixels, red, green, blue values, and you're going to turn that into a vector. I hope this is enough to continue what SIFT is doing. So now you can associate every single patch in your images to a vector. And these are your local descriptors. Now you take each descriptor in your entire data, and then you're going to do a clustering. You're going to cluster them into K vectors. This is being done for your entire data set. And your clustering algorithm could be a Gaussian mixture model. So you do clustering. What is next? Somebody is going to give you an image. It's going to constitute a bunch of patches. You take the patches in your image and then look at the nearest neighbor of xi for that particular patch. And if it is mu k, mu are the centers of those clusters. You're just going to compute the difference of that xi minus mu I. So this summation and this set is just trying to find the nearest neighbor for this particular patch, which mu k was the closest to this one, in order to be able to do the subtraction. These are the first order differences. We can look at the second order differences as well, which is going to be the square of that. And this is just accumulated second order differences. Now you're going to concatenate all of these vectors that you found. u1, v1, u2, v2. You're going to have k of them for the first order differences. You're going to have k other ones for the second order differences. That's going to give you the 2k here. And then each vector, each one of these local descriptors that are coming out of your sieve are going to be d-dimensional. And that's going to be your feature or Fisher vectors corresponding to this particular image. And this is what feature engineering means. But then what is the improved about? What are you improving? You take those vectors coming out of those Fisher vectors, you take the sign of it, square root of the absolute value, and then you push them through L2 normalization so that they have a unit norm. And then that's going to give you some improved vector representations for your image. That's feature engineering, and the entire process here corresponds to this function phi. We can train a deep neural network and let phi to be a deep neural network. And these are the activations at some particular layer. This could be the layer, the last layer, or the layer before the last one. So that's what deep learning does. That's what feature engineering is doing. A lot of intuition, looking at the local statistics of your patches and then aggregating them so that you can look at an image and compare it to similar images in your data. And that's where the clustering is coming in. This is with pre-training. You pre-train a convolutional neural network on a specific task. If you do pre-training and fine-tuning, you are entering into the realm of transfer learning. So there is a question in the chat. This seems more, or this seems somewhat similar to principal component analysis. Is that the correct way to be thinking about this? About which one? About improved Fisher vectors? It is more related to the clustering. So it is actually a clustering algorithm. So you first find the cluster centers, and then you look at every patch in your image, compute its distance to the cluster centers, and then aggregate them, or aggregate the square of them. So now it's a lot more complicated than what you would do with PCA, because PCA is going to give you a linear representation. It's going to be basically you take your image, multiply it by a matrix, project it into a lower dimension. That's it. So in that case, your phi is a linear function. But here you can see your phi is really complex. Not only you're looking at this particular image, you're looking at the centers of the clusters that are a result of looking at your other data set, the entire data set. This is feature engineering, feature learning. That's their story. And that's all I wanted to cover from this paper. The rest of it is just, again, transfer learning. Not only your feature vector, your Fisher vectors are transferable, the features that are coming out of CNNs are also transferable across tasks. For ImageNet, for Pascal VOC, for Caltech 101, Caltech 256. The only one that is different here, all of them are in terms of accuracy. One of them is mean average precision. That one I'm going to cover later on when we do object detection. But for now, what is the difference between the images that you see in Pascal VOC versus the images in ImageNet? There could be multiple objects in one image, and you want to identify all of them. So it's not one class per each image. There could be multiple classes per each image. How do you actually do your transfer learning here? You cut your CNN at some layer, and on top of that, you're going to put a head. This is a multi-label data set, Pascal VOC. You're going to define some positive images and some negative images corresponding to a particular class. Because now if you pick a class, there could be multiple of them in your images. For instance, if you pick a dog, there could be one image that contains a dog, another image that doesn't contain it. You pick a cat, this image that already contained the dog might also contain the cat, and then you can define some negative examples of images that don't contain a cat. So that's how you're going to define your positive and negative cases. And then you're going to do one versus rest classification using a hinge loss. What is that loss? For the positive cases, you take them, a positive image, you push it through your neural network, you stop at some particular layer, you multiply it by a matrix of the same size or by a vector of the same size, so that this number, this is a dot product, ends up being a scalar. If it is bigger than 1, forget about KC for a second. If it is bigger than 1, your model is doing the right thing because this was positive. There is that particular class included in this particular image. And in the other case, it doesn't exist. And you do it with a margin, the ones who are bigger than 1 and the ones who are less than -1. And that's where the hinge loss is coming in. Hinge loss, you usually use it for support vector machines, but here you can use it as well. And then you want to be a little bit relaxed. You don't want to be too strict. You're going to give a slack to this 1. It's okay to be a slightly less than 1 and a slightly bigger than -1. That's fine. Or alternatively, you can have the ranking hinge loss. Rather than having 2 separate objectives like that, you can have a single objective. And you're separating the positive examples from the negative examples with some margin, and then with some slack. You're relaxing your constraint a little bit. And then what are you training here? This is my question for you. What are the parameters that you're optimizing over? This is going to give you your loss function. You write it down for every single image. You do a summation over your data. What are we optimizing over? So I'm going to give you 2 options, and then you answer them. Are you optimizing over the parameters of phi, or are you optimizing over W's? Yes, so your primary object of interest are these W's. You're optimizing over them. At the same time, you can do some fine tuning. So these are pre-trained. Phi is going to give you your features. And one of you answered the clusters. There are no clusters here. So what I was going through here was 2 totally different approaches. And now we are going the CNN route. To obtain the features, the improved feature vectors, we had to do feature engineering. So there are no clusters anymore. So forget about that. Okay, that's gone, because that's part of your feature engineering process. Once it's done, it's done. It's like part of training your convolutional neural network, pre-training it. Once it is done, it is done. You can only fine-tune it. Does that answer your question? And then there is another one in the chat. For a multi-label data set, isn't it the same as classification, except we don't have the restriction that the probabilities add up to 1? Yes, you're correct. So this is exactly classification, but it's multi-label. Each image could have multiple labels. So a soft max is not a good last layer for us anymore. And cross-entropy loss is not a good loss for us anymore, because for them, your probability distribution needed to add up to 1. It means there is only one object that's going to dominate. So here you're going to reverse your thought process. Rather than looking at images and then predicting the corresponding class, you're going to pick a class, look at your images, and label them. Is this a positive case for this class? Is this a negative case for this class? And then you do your training this way. And then the second part of your question is, can we still use categorical cross-entropy, but we'll just have labels with more than one entry as 1? I guess you are asking, rather than doing softmax in the end, can I do sigmoid? And then it's not necessary for them to add up to 1 anymore. And then write down a cross-entropy loss. Yes, you can do that. That should be fine. Does that answer your question? Okay, perfect. But this is how you're going to transfer. You have to rethink how you're going to do, what is going to be your transfer learning objective. And that depends on the data that you choose. So this figure or this table is a little bit confusing, and I have no intention of going into details because there's a lot of codes specific to the paper. Like this is a spatial pyramid pooling, or this is F is when you're doing the data augmentation, that is flipping your images left and right. C is when you're cropping in addition to flipping. S is when you're doing sum pooling or average pooling. M is when you're doing the max pooling. Maybe in the end, your CNN is giving you a bunch of features, a bunch of vectors per each pixel, and then you can average them out like global average pooling. or you can do the maximum of all of them. So it's a lot of details, and it's those details. But the big picture from this table is that, yes, if you do the sort of tricks that you do to improve a convolutional neural network, you can do the same sort of tricks to improve the representations that are coming out of a shallow method, a classical feature engineering method. For instance, data augmentation helps a lot in both cases, but then it is still helping CNNs more. The features that are going to come out of CNNs are going to end up being much better. So that's the big picture. And there's this trend prior to 2012, right around here, people were still using these Fisher kernels and histogram of oriented gradients, doing a lot of feature engineering. And this was the performance that they were getting. This is for Pascal VOC. This is mean average precision. But then starting with deep learning, things are starting to improve. And there seems to be a plateau here, but then deep learning is helping us do much better. Any questions about this? So first of all, I thought you're gonna appreciate more if I tell you the difficulties people had to face prior to deep learning and how you can simplify that with an end-to-end framework rather than having different steps. The other one was telling you the difference between feature engineering and feature learning, at least give you the big picture. The other one was if you want to do transfer learning, you cannot do it blindly. You cannot say, I trained a model on ImageNet. I'm going to take the same model with 1,000 classes and then apply it to a data set that has only 10 classes. Or it's a multi-label type of a data set. You cannot do that. You have to modify the head of your neural network a little bit. And the other one was that details matter. Like data augmentation is really useful, not only for deep models, but also for feature engineering type of models.